Yes. So this is a preview for the session called Mechanized Proofs. The general field is formal methods where you want to have very strong guarantees that your software satisfies some properties. So there are different fields in formal methods, and here we will have a paper on defining a type system for ensuring properties, and 3 other papers that will use deductive verification. So let me first introduce terminology related to the paper and the tools that will be used, as they share the same goals, but they do it in a different way. So when you do deductive verification, you want to ensure that your software is correct with respect to your specification. And for that, correct means correct in the mathematical sense. So in order to show this correctness, you construct a proof, and you can replace this proof or give it to an authority that can read it, for instance. So this proof, once you have this proof, in the end, your goal is to have a verified software, meaning that you have 2 parts. On the one hand, the implementation, and on the other hand, the proof that your software satisfies some property. So when you have a verified software, the property is related to the language that is used in the software. So you need to reason on this language in order to show your properties. And for this, if you want to have mathematical guarantees, you need to have a formal semantics for the language you are interested in. So in order to reason on realistic languages, so you will not write proof by hand, you will use proof tools. And there are mainly 2 families of proof tools. On the one hand, automated tools that discharge some formula to external solver, for instance, SMT solvers. And these tools are easier to use when there is no extra work for the user, but it may be necessary to add assertion in order to help the prover to prove the expected properties. So when it becomes difficult to prove these properties, so you may use interactive proofs where the user is deciding on which to reason and how to conduct the proof. So here, the 4 paper will use deductive verification, and they use the code proof assistant in order to have proofs. And the papers are also related to 2 different automated provers, the Y3 tool and the VST tool. So the first paper is about, the goal of the first paper is the long-term goal is to verify one of these tools, to verify the Y3 automated prover. And this paper is the first step towards this verification. So when you use Write3, you do contract-based programming, meaning that you write specification using contracts, pre- and post-condition, and then you write your program, and you want to show that your program satisfies the specification. So in this paper, they verified the logic fragment of a small subset of Write3. The logic fragment is a logic language used to write your specification. So they defined an operational semantics in Coq to reason on this language. And then they validated these semantics, and they showed the correctness of some program transformations. They showed, on the one hand, some operations that are in the Y3 library that usually are proven in Coq and not directly in Y3. And moreover, they showed the correctness of elementary transformation, because when you use automated proof, you have goals, a formula to prove, and what the tool does is simplifying this formula, and in the paper they prove 2 of them. So the second paper has a different approach. Here the goal is to have a very rich type system with refinement types. So you want, here your properties are encoded in the types, so you write a program with very rich types, and here once you have all these types, then you need a type checker in order to check the validity of the property you wrote in your type. So here they design a type checker for a new refinement calculus. So this extends some previous work with new features. And here they can express richer properties. And this is done without requiring extra work from the user. So you can express more property, but the tool is able to prove them alone. So the paper defines the meta theory for this new core calculus. So here the language is lambda calculus, and they show they define a new type system, and they show the soundness of the type system. In particular here, because you have rich property refinement types, so there is a notion of semantic subtyping that will be presented in this paper. And here the properties are discharged to SMT solvers and then prove this. And in this paper, they did two formalizations, one with the Coq proof assistant and another one with the liquid Haskell language. That this calculus has been implemented in liquid Haskell, but when they mechanized all what they did, they realized that they could not express everything in liquid Haskell, so they did another formalization using Coq, which was an opportunity to compare the different formalization. A third paper here is about verifying compilation. So this is so in verified compilation, you have the COMCERT-C compilers that compile C programs down to assembly programs. It is approved in Coq. Here they extended the compiler in order to allow compilation of independent modules. So in COMCERT, you can only compile C programs. Compilation is a series of compilation passes, so you can only compose sequentially the passes. And here, this idea is to have something more general. For instance, if you want to compile a C program with some library, including calls to assembly functions, for instance. So here they define the general notion of refinement and language interface. What do we need if we want to compile independent modules? So this is an extent. There have been several papers on that subject, and here they improve previous approaches. And what they will describe in the paper is the expected properties for proving this thing. This notion of vertical compositionality that already exists in COMCERT, but also horizontal compositionality and notion of adequacy. And they explain in the paper how the three can be used together. And the last paper is shares the same goal as the first one. The idea here is to verify another program logic, which is a VST. This logic handles a real C program. It uses the C-like language of the COMCERT compiler. So here you want to do automated proof on C programs, like with Y3, but the language is more complex. So here, usually in VST, it's not automated at all. So in VST, you need to do the proof interactively with Coq. So what they did in this paper is a more automated alternative to VST in order to be able to do things like what you can do with Y3 that targets a simpler language. And so they design an annotation verifier in order to be able to prove automatically some annotations. And here this is done in Coq, and they explain in Coq how to decompose the formula, exactly this is the same that is done in Y3, but here the language is different. So they showed the correctness of some program transformation to reduce assertions. And in the end, they have a soundness theorem that states that the program is correct if all the decomposition they have at every program points have been verified. That's it.